Hello, I am Sajesh Vilaharan. We are from Group 26. We are going to present about analysis of fluid flow and heat transfer for an airplane tail. So I am Sajesh Vilaharan. With my friends, we would like to present for this topic. Introduction. The concept of natural stability refers to the ability of an aircraft to return to equilibrium state. This function is generally provided by the airplane's tail or FNH, which generates an aerodynamic force located at the aircraft's center of gravity and then restores a moment that allows the aircraft to be naturally stable. For this project, we have used computational fluid dynamics software to examine and analyze the simulation of the airplane's tail. Objectives. Our objective is to calculate the shear stress acted upon the airplane's tail and also to analyze the effect of fluid flow on heat transfer on the FNH surfaces. So we have used CFD software to analyze this.
Next, I want to talk about the methodology. The first step for this study is to construct the desired geometry for an empennage surface. By using Boeing 777 airplane as a reference model, the geometry is built using Autodesk Inventor Professional 2022. To achieve the main objective, the drawn geometry is only focused on the airplane tail by assuming air resistance occurs directly on the tail surface, regardless of the front part of the airplane. This move also aims to save usage of the number of elements and nodes due to limitation of the licensed version. Next, the airplane tail geometry is then imported to ANSYS workbench. Also in this part, input, output, symmetry plane and wall for the whole geometry are declared. The next step is to create a cube enclosure as a domain with a size of 27.8 meter times 16 meter times 37 meter. Then, boolean is added with target and tool bodies declared. The meshing process is then started. The material chosen for the airplane surface is aluminium. It's high resistant to corrosion and good weight to strength ratio make it perfect material for aircraft construction. The plane should be observed in two situations. One, while flying at height of 30,000 feet at a speed of 800 km per hour, and two, when it is at ground level during takeoff condition travelling at a speed of 296.32 km per hour.
We move to the result. The shear stress value ranged from 85 Pascal to 0.8 Pascal for the 30,000 feet, 800 km per hour situation, with the rear of the airplane's tail experiencing the largest value. The pressure on the surface of the aircraft ranged from 12 kPa to -7 kPa, with the horizontal stabilizer face producing the most pressure. This is the airflow velocity contour across an airplane's tail surfaces where the existence of turbulence wake can be seen. The temperature value for the airflow is between 229 Kelvin and 228 Kelvin according to the temperature streamline. The value of the wall heat flux range from 21 to 147 watt per meter square. The residual and drag coefficient results are then computed, and over a number of iterations, the number tend to approach constant value after several computations.
The result for the ground level at speed 296.32 km per hour, the shear stress value is between 11.16 and 0.121 Pascal, and the higher value is at the middle of the tail of airplane. The value of pressure is between 1,597.124 and negative 36,663.755 Pascal. The value is higher at the middle of the tail. the highest value of velocity is at 81.815 meter per second. At the temperature streamline, the value is between 298.4 and 298.1 Kelvin. The next value is heat flux. The heat flux value is between 1158.391 and 60.968 watt per meter cube. Lastly, the result of residual and drag coefficient iterations of the airplane is decreased when the iteration increase.
For the discussion, there is the presence of turbulent wake at the end of streamline as the flow is turbulent, which we can see from the figure of velocity streamline. The difference shear at 3000 feet and 800 km per hour and during takeoff shows us the significance of lift analysis, which shear effect can be neglected if the Reynolds number is above than 10,000. The difference between shear effect and pressure effect, as the pressure plays the major role for the lift force. The significance of dynamic temperature at high altitude under high speed affect the heat transfer, as the heat transfer is correlated with the wall heat flux, with the equation of heat transfer equals to the wall heat flux per area.
In conclusion, the foregoing discussion has shown that the shear and pressure are the important parameters that exert the force on the airplane. The maximum shear stresses acted upon the airplane tail is 74.9 Pascal and the minimum shear is 0.296 Pascal for wall shear. Shear stress is less significant if the velocity of the airplane is higher. The significance of study for tail design and innovation to reduce freezing shear effect is important because the temperature is directly proportional to the pressure. The effect of fluid flow on the heat transfer of the empennage surface is the heat transfer coefficient of the surface will increase when the fluid of velocity increase.